In this lecture, I will basically discuss how to test for restriction using GMM criteria function. We use difference between the constraint and unconstrained criteria function, and we take the difference between the minimum value of the criteria function in the presence of restriction and without the restriction. We next discuss some important facts about the GMM estimator. Good morning everybody. In the last class we have discussed the concept of feasible efficient GMM estimator. Now let us note that since OLS estimator belongs to the family of GMM estimator, the feasible efficient GMM estimator can be used when all the columns of the explanatory variable x are valid instrument, and hence OLS would be the estimator of choice if the error terms were not heteroscedastic and or serially correlated. So in this case, W typically consists of x augmented by a number of functions of the residual on the diagonal. So if you find that x's are heteroscedastic or x's are not heteroscedastic or are not serially correlated, then W can be taken as the matrix X or augmented by the number of functions of the residuals of the diagonal. Now just as in the case of generalized IV, you can carry out the test of linear restriction in this GMM model. So in the next step, let us discuss how to test for the linear restriction using GMM specification. Now, as in this case also, you can take both linear as well as nonlinear restriction on the regression model, and you can carry out the difference between the constraint and unconstrained minimum of the GMM criteria function as a test statistics. So while carrying out the test for linear restriction, what we can do? We can first estimate the model using the restriction and estimate the model without using the restriction, and can take the difference between the constraint and unconstrained minimum of the GMM criteria function as a test statistics. Now under weak condition, this test statistics is asymptotically distributed as a chi-square with as many degrees of freedom as there are restricted to be imposed. Now let us consider the regression model y equal to x beta plus u, where y is the dependent variable, x is the explanatory variable, and b is the parameter to be estimated. Now in this case, you can decompose xb as x1 b1 plus x2 beta 2 b2. So you can write y equal to x1 b1 plus x2 b2 plus u, where b1 is a k1 vector and b2 is a k2 vector with k is equal to k1 plus k2. And we like to test whether the k2 takes the restriction b2 is equal to 0. So what we do, you first estimate the model x1 b1 plus x2 b2 plus u, and then after estimating the parameter b2, you use to test the restriction beta 2 equal to 0. So if we estimate the expression by feasible GMM estimate using W as a weighing matrix, or matrix of instrument subject to the restriction beta 2 equal to 0, we obtain the restricted estimate. Therefore, if you take the difference between the constraint and unconstrained minima of the criteria function, and test statistics is a chi-square distribution with k2 degrees of freedom under null hypothesis H0. So what we do? We basically estimate the restricted version of the model and the unrestricted version of the model, and then take the difference between the unconstrained minimum of the criteria function and the constrained minimum of the criteria function, and this should follow under H0 a chi-square distribution with total number of restrictions which is equal to k2. Now the result will be valid if the restrictions are nonlinear as well. So this criteria can be applied either if the restrictions are linear or the restrictions are nonlinear. The requirement that the difference between the constraint and unconstrained minimum of the criteria function to test statistics is asymptotically chi-square distribution with k2 degrees of freedom under H0 depends on the two crucial features of the construction of the test statistics. That is, two sets of assumptions are very crucial while getting the result. The first is that the same wing matrix W is used for estimating both the restricted and the unrestricted model. That is, you are using the same instrument matrix W while estimating both the restricted as well as unrestricted version of the model. Now the second feature that is needed is the same wing matrix is needed for estimating the model. If the different instrument or different wing metrics are used for two models, the difference, the optimum value of the constraint criteria function minus the optimum value of the unconstrained criteria function will no longer in general be asymptotically distributed with chi-square k2 degrees of freedom. So what we need, first of all we use the same instrument both in the case of constraint as well as unconstrained function, and secondly you need to use same wing matrix both in the case of constraint and unconstrained minimum. Now one interesting feature is that we do not always need to bother estimating the unconstrained model. To consider this, suppose that since the optimum value of the unconstrained criteria function is always positive, if the optimum value of the constraint criteria function is less than the chi-square k2 at our chosen level of significance, we can be sure that the actual test statistics is even smaller and would not lead us to reject the null hypothesis. So to start with, if the estimated optimum value of the constraint criteria function is less than the chi-square with less than the tabulated value of the chi-square with k2 degrees of freedom at the chosen level of significance, that automatically would lead us not to reject the null hypothesis. That is, in this case we accept the null hypothesis that H0 k2 is equal to 0, beta 2 equal to 0. The result that test of restriction may be based on the difference between the constraint and unconstrained minimum of the criteria function holds only for efficient GMM. So the above results hold only if you are using efficient GMM estimation. It is not true for non-optimal criteria function which do not use an estimate of the inverse of the covariance matrix of the sample moment as the weighing matrix. So if you use non-optimal criteria function, then the above result will not hold. Now when GMM estimate minimizes a non-optimal criteria function, the easiest way to use the restriction is probably by using a wall test. So GMM type of restriction can be used if and only if the used. So result that the test of restriction may be based on the difference between the constraint and unconstrained minima of the GMM criteria function holds only for GMM estimation, or only for efficient GMM estimator, and hence it is, if it is not true, hence it will not be true for non-optimal criteria function which do not use an estimate of the inverse of the covariance matrix of the sample moment as a weighing matrix. So if you have non-optimal criteria function, the above results of the likelihood function will not hold. Now, when GMM estimate minimizes non-optimal criteria function, the easiest way to test the restriction is probably by using a wall test. Now, in the next, let us consider nonlinear model. Now, estimate the model by nonlinear instrumental variable and may solve the standard iterative nonlinear instrumental variable, estimate the covariance matrix. Now, minimize J by using nonlinear optimization and iterate the covariance matrix to get the optimal covariance matrix. Now, let us note some useful facts about the estimation process. Covariance matrix estimator must be positive definite, asymptotically true, and it has to be shown that the quadratic spectral window is the best. Secondly, in small sample, Nive and West 1994 show that little difference between the quadratic and their estimator based on Bartlett. So, for this small sample, there is practically little difference between the quadratic and their estimator based on the Bartlett function. Now, choice of the bandwidth parameter is more important than the choice of the kernel. Now, variable Nive and West and induced state of art. Now, hack estimators suffer from poor small sample performance. Thus, test statistics, for example, t-test may not be reliable. These statistics appear to reject a true null far more often than their minimal size. Now, adjustment to the matrix W may be more, but this depends on whether there is autocorrelation and or heteroscedasticity. That is, the choice of the W matrix basically depends on whether you have the case of autocorrelation and or heteroscedasticity. Now, numerical optimization, common problem of not having a global maximum or minimum. For example, problem of local maximum or minimum or flat function. Without a global minimum, GMM estimation does not yield consistent and efficient estimate, and convexity of the criteria function is important. It guarantees the global minimum. So, what we get? The numerical optimization common problem of not having a global maximum or minimum, and for example, the problem of local maximum or minimum or flat function, and without global minimum, GMM estimation does not yield consistent and efficient estimate, and convexity of the criteria function is also important. Basically, the convexity problem guarantees the situation of global minimum. For non-convex problem, you must use different method. A multi-start algorithm is popular. Start at a local optimization algorithm from initial values of the parameter to converge to a local minimum and repeat the process a number of times with the different starting value. The estimator is taken to be the parameter value corresponding to small values of the criteria function. However, it does not find the global minimum. So what we find, the estimator is taken to be the parameter value corresponding to the small value of the criteria function. However, it does not find the global minimum. Andrews 1997 proposes a stopping rule procedure to overcome this problem. There is a weak instrument literature. Nielsen and Starrs 1990 considered instrumental variable estimator have poor sample property when the instruments are weakly correlated with the explanatory variable. So, if you have a weak correlation of the instrument with the explanatory variable, as suggested by Nielsen and Starr 1990, you see that instrumental estimator have the poor sample properties. And secondly, chi-square tend to reject the null hypothesis too frequently as compared to its asymptotic distribution. So in this case, what we find? We find that chi-square test will tend to reject the null hypothesis too frequently compared to its asymptotic distribution. And T ratios are also too large. Hansen 1985 characterizes an efficiency bound for the asymptotic covariance matrix of the alternative GMM estimator and the optimal instrument that attain the bound. So, Hansen 1985 characterizes an efficiency bound for the asymptotic covariance matrices of the alternative GMM estimator and the optimal instrument that attain the bound. Finite sample property of GMM estimator similar to weak instrument literature. Taushen 1986 and Kocher-Kota 1990 examine artificial data generated from a nonlinear capital asset pricing model. Using two-step GMM estimator, Taushen concluded that GMM estimator and test statistics had reasonable properties in small samples. He also investigated optimal instrument, finding that optimal estimator based on optimal selection of the instrument often do not perform as well in small sample as GMM estimator using an arbitrary selection instrument. So, Taushen has investigated optimal instrument, finding that optimal estimator based on the optimum selection of instrument often do not perform as well in the samples as GMM estimator using an arbitrary selection of the instrument. Kocher-Kota 19 allow for the multiple assets and different sets of instrument using iterated GMM estimator. Kocher-Kota finds that GMM performs worse with larger instrument, leading to downward bias in the coefficient estimate and narrow the confidence interval. Also, the J test tends to reject too often. So, you may not obtain always desirable property of GMM estimator under certain condition. Furthermore, and Schuss 1995 compared the GMM and the maximum likelihood estimator in a class of nonlinear model using Monte Carlo simulation. They find that GMM estimate tend to reject their model while ML support it. Why? As Moore and Schulz find out that GMM estimates are often biased, statistically insignificant, economically implausible and dynamically unstable. They attribute the result to weak instrument condition. Finally, there may be the problem of non-stationarity. The data must be maybe non-stationary, and in this case, in order to use the GMM, you have to check for the stationarity. So, data may be differenced or co-integrated, and in this case of co-integration, Kohli and Ogai suggest estimating the co-integrating relationship using OLS and use this parameter for the covariance matrix of W. So first you have to check the stationarity property of the data after applying the GMM estimator. So before applying GMM estimator, you need to check the stationarity and co-integrating property of the series in order to get the better result. In this lecture, we have discussed how to test for restriction using GMM criteria function. In order to achieve this test, you basically need to estimate the criteria function twice, first of all with restriction and without restriction, and then you need to take difference between the minimum value of the criteria function with and without restriction. It can be shown that the difference between the constraint and unconstrained this value of the minimum value of the criteria function will follow a chi-square distribution with where the degrees of the freedom of the chi-square distribution is equal to the number of restrictions available in the model. We end the discussion with highlighting some useful facts regarding the method of estimation using generalized method of moments.